This lecture is sixth lecture, sixth topic of enolates, and we're going to be talking about something called Michael reaction. And to introduce you to that topic, we have to look at what we've been doing so far. So far what we've been reacting with is a carbonyl, in which the carbon of the carbonyl was partially positive. So therefore we had a nucleophile that, in this case enolate, came and attacked the carbon of the carbonyl, and the reaction proceeded. So this right here, you would call that a direct addition of the nucleophile. Is directly attacking the C-double-O, and a lot of times this is called 1,2 addition. All right, and I'll go over where this number came from. All right, so what happens though, so this is like an isolated C-double-O. In other words, the carbonyl is not a part of a conjugated system. So now what we're going to look at is, in this lecture, not an isolated carbonyl, but a conjugated carbonyl like this, in which we have an alpha-beta unsaturated ketone connected to C-double-O. So here, it actually has two choices. So this is alpha-beta unsaturated carbonyl, and another name that is often used is enone if it's a ketone. So this kind of compound, when it's serving as an electrophile, it has two choices. All right, and the two choices that the nucleophile could come in and attack in a direct addition at the carbon of the carbonyl, or so this would be 1,2 addition, or it could do what's called a Michael addition, which attacks at the this beta carbon, and that's called Michael's addition or 1,4 addition. So those are the terminologies that is used. All right, so why, when you have all of a sudden a conjugated system, does it attack does it attack at the beta carbon? All right, so in order for us to understand that, we need to look at the reactivity, the unique reactivity at the beta position, and to see this, you have to draw the resonance structures of these compounds, which is shown here. So these are the resonance structure of the alpha-beta unsaturated carbonyls. So you know that one resonance structure is that the double bond, you put it on the oxygen, so you have a negative charge on the oxygen and a plus charge on the carbon. All right, but when you draw that, you know that you could draw another resonance structure in which the double bond moves over to that carbon, which causes this beta carbon, so that's the beta carbon, to be a positive charge as well. So if the double bond wasn't there, you know that the only resonance structure we could draw is the CO, where the double bond is moved, the electrons are moved to oxygen, but because of the double bond being next door, you know that we could draw a resonance structure like this. So what does that tell you? It tells you that the beta position, which is right here, is reactive, and how is that reactive? Is electrophilic. So in this conjugated system, there are two electrophilic positions. Okay, one at this carbon, which is drawn by this resonance structure with this positive charge, and the other one at the beta. So the two electrophilic sites are, once again, the carbon of the carbonyl, that's where we did all our reactions so far. But then the beta carbon is also electrophilic. And the way the 1,2 versus 1,4 came about, I think is the way they number it. This got nothing to do with nomenclature or anything, but this is 1,2, and then the relationship is 1,4 between the oxygen, so that's why it's called 1,4 addition versus 1,2 addition. All right, so the nucleophile is going to be attracted to these two different sites. All right, so here's what is shown above there, in which the top is the simple addition or 1,2 addition, and the bottom is conjugate addition or 1,4 addition. So there are a lot of names for this: 1,4 addition, Michael addition, and conjugate addition. These are the three names that are referred to for the 1,4 addition. So then let's take a look at the 1,2. So then that means this would attack here, and then you would have this kind of intermediate. Whereas if this attack here in the beta position, then the double bond has to move over and then break the C double bond O. So the intermediate after the nucleophile forms is an enol, and as you know, the enol will exist in equilibrium with the keto form, and depending on which is more stable, you have more of the other. All right, so what determines whether or not nucleophile attack 1,2 versus 1,4? All right, and that is determined by the nucleophile, the basically the identity of the nucleophile sort of determines whether or not it's going to be added in a 1,2 fashion versus 1,4 fashion. So the nature of the nucleophile is what's important. So we're going to list the nucleophiles that prefer to add 1,2 versus 1,4. All right. So it turns out that Grignard's nucleophiles and hydrides, all right, tend to attack directly at C double bond O carbon. All right. Whereas the nucleophiles that are a little bit more not as hard, such as cuprates. So you've seen these before. Cuprates tend to add 1,4, and the cyanide ion tends to add 1,4. Amines tend to add 1,4. So we got cuprates, cyanide, and amines. Enamines, which we're going to go over how that they could act as a nucleophile. We haven't gone over that yet, so this is a little bit later. And then enolates. All right, but there's a difference in the enolates. So enolates has to come from a doubly stabilized enolate, where the Z and Z prime are electron withdrawing groups. All right, so for example, what you just learned with malonic ester enolate would be classified under this, or the acetoacetic ester would be also qualified for this. And then remember, we went over all these different two different electron withdrawal groups you could have. All these would qualify as the enolates that's got double electron withdrawal groups, making this enolate more stable than a different normal kind of enolate. So those tend to add 1,4. All right. So anything, the nucleophiles that add 1,4 are called Michael donors, and the electrophiles, so for example, any alpha beta unsaturated compounds, they would be called Michael donors. I mean acceptors, because they're accepting the nucleophile. So these 1,4 nucleophiles, all that are listed here, are Michael donors, and the alpha beta unsaturated would be called Michael acceptors. All right. So so basically, you just kind of have to know that most nucleophiles, other than Grignard and hydride, tend to add 1,4 if you are reacting alpha beta unsaturated compounds as your electrophile. All right. So here's a typical mechanism of 1,4 addition with real nucleophiles. So here's an amine, and what it's showing here is the partial positiveness of this carbon and this carbon. So because this amine is a Michael donor, it's going to attack the beta carbon. It's going to cause the double bond to move over and C double bond O to break and form this O minus. So you should draw a bond between the nitrogen and the beta carbon. So that's the bond that you make, and notice this is like an enol version, especially after it gets protons. So here's the enol form after it had the nucleophiles attacked, and then the keto form, which is a tautomer of this, will coexist, and in this case this is the more stable form, so that's why the equilibrium lies to the right. Okay, so I would expect you at this point to do on the next page drill, which is all of your substrates are alpha beta unsaturated, and you need to look at the nucleophiles and ask yourself, is it a 1,2 or a 1,4 type of nucleophiles, and then give me the products on the right hand side, what the product will be. So anyway, so there's several of these, and then at the end I would like you to do 22.44 from your book as well. So these drill problems plus 22.4 for this lecture. All right, and that concludes the Michael reaction, and we will continue on with the Stork-enamine reaction.